Chapter 5 is about stereoisomerism. So, chirality is a very important concept in organic chemistry. Some molecules are said to have handedness. If you think about your hands, I think everybody here has two hands, right? So we've got two hands, and if you look at them, they're the same, and yet they're different, right? And think about a glove. Can you put a left-handed glove on your right hand and have it fit well? No, because they're not the same. You can't superimpose your hands, but they are mirror images of each other. If you put one hand in the mirror, like they're showing in this picture, it looks just like, here you put your left hand up to the mirror, and the mirror image looks just like your right hand. So your hands are different, and yet they're the same, and some molecules are like that as well. So we say a molecule is chiral if the mirror image of it cannot be superimposed on the molecule itself. An achiral molecule does not have handedness. So here we have a picture of a ball. The mirror image of a ball is the same, isn't it? You can superimpose the mirror image on the object. There's no left and right hand to a ball. They're the same. The mirror image is the same. So let's think about these everyday objects and identify which are chiral and which are achiral. And depending on your life experiences, you may find some of these less obvious than others. What about a golf club? Golf clubs are chiral because there are left-handed golf clubs and right-handed golf clubs. What do they call the part at the bottom? The head, yes. The head of the golf club is shaped differently on each side. It's not the same. And so if you try to putt right-handed with a left-handed golf club, you're going to have a hard time. So a golf club is chiral. How about a teacup? A teacup is achiral. You've got the round teacup and it has a handle, but it doesn't matter which side of it you drink out of it, it's going to be the same. How about a football? A football is achiral. How about a corkscrew? A corkscrew is chiral. If you turn it one way, it will screw into the cork, and if you screw it the other way, it will screw out of the cork. It has a direction to it, right? So a corkscrew is chiral. How about a tennis racket? Tennis rackets are achiral. Have you ever heard of a left-handed tennis racket? No, because they're the same on both sides, right? How about a shoe? Shoes are chiral. There's a left shoe and a right shoe. How about a portrait? Is the mirror image the same? It's backwards, right? One of the interesting things, there's all these selfies and stuff that people post on the internet, and some people just point the camera at themselves, and other people are taking pictures of themselves in the bathroom. Why? It's always the bathroom mirror. Who wants to see a picture of your friend in the public restroom? But have you ever noticed that when you look at a picture of yourself, you're like, do I really look like that? And that's because you are accustomed to seeing your face in a mirror. You're accustomed to seeing the mirror image of your face, which is not exactly the same. Yes, you have an eye on each side, but they're not exactly the same shape. And you've probably seen those things where they take and you cover up one side of a person's face and they may look very sinister and they look real friendly on the other side. Okay, so your face is not completely symmetrical. So I would say that a portrait is chiral. How about a pencil? Achiral. So you get the idea? See, I'm a left-handed person, and so I encounter a lot of chiral objects in life. A teacup is achiral, but those measuring cups are actually chiral because they have the metric units on one side and the English units on the other side. And since all the recipes in the cookbook use the English units, I always have to turn it around from the way I would like to hold the measuring cup. And playing cards. Playing cards are chiral. They have the little numbers on the upper right so that a right-handed person can fan them out. I can't fan them. And so I have to do them one at a time unless I get left-handed playing cards which have the numbers in all four corners. It's all these little things.
Knives?
Some knives are, yeah, they're
Like for left or right-handed?
definitely. And those can be so frustrating because we have some of those and I've just learned which ones they are and I never use them because they always go off in the wrong direction for me.
Yeah, I know I'm left-handed and my boyfriend always gets scared when I try to cut stuff. He's like, he just, I don't know, I guess because the way I cut it's weird, so he would get scared.
Yeah, and scissors and there's a lot of things. Okay, next slide. So some molecules have handedness. Let's look at 2-chloropropane. So here's a model of 2-chloropropane. So here's 1 carbon, 2 carbons, 3 carbons. That's the propane. And there's 1 chlorine on this carbon, and here's a hydrogen. So if we look at the mirror image of this molecule, we could take that mirror image and just rotate it around and superimpose it on top of this other molecule. The molecule and its mirror image can be superimposed. There's only one possible structure. If we look at 2-chlorobutane, so here we've got 2 carbons, 3, 4, so this is butane, and a chlorine on the second carbon, so we've got a hydrogen, a chlorine, a methyl group, and an ethyl group if we're just looking at this carbon. And here's the mirror image. When we take that mirror image and bring it around, it's not superimposable. So there are 2 different structures. There are 2 possible structures, and we say that these are enantiomers. Enantiomers are molecules that are related as non-superimposable mirror images. So a carbon that has 4 different groups, and the 4 different groups is what's really important. 4 different groups attached to it is called a stereogenic carbon or a stereogenic center. I'm going to try to use that terminology because that's what your book uses, but I've always talked about them as chiral carbons. So I may slip and say it's a chiral carbon. But when we have a carbon like this that has 4 different groups, here we've got methyl, chloro, ethyl, and hydrogen, 4 different groups, then the mirror image is not superimposable with the original molecule. These are enantiomers, and this carbon is said to be stereogenic. Stereogenic, genesis, giving rise to stereoisomerism. So these are stereoisomers. And we can represent this isomer. Here's the carbon, and you see the D and the E are kind of poking out at you. Those are the wedges. And the dashed lines are going behind the plane. And this one can be represented like this. The A and the B are in the same position, but the D and the E are switched. So those are stereoisomers. If we have 2 of those groups being the same, the molecule is achiral. The mirror image is superimposable. And that's because a molecule in which the carbon has 2 identical groups on it has a plane of symmetry. So if we look at this molecule, there is a plane of symmetry including D, B, and C, and it cuts between A and A. The molecule is the same on each side. There's a plane of symmetry. So chiral molecules do not have a plane of symmetry. So let's look at these molecules and identify the stereogenic centers. What we're looking for is a carbon atom that has 4 different things attached to it. And some of these we're going to have to draw out because we can't just look at the formula. So this is a condensed structural formula. Which carbon do you think might possibly be chiral? Anything with H2 or H3 couldn't be, right? So it would have to be this one. So let's do this. Instead of having the hydrogen here, let's draw it out there. And then I'm just going to kind of move this bromine so it's up here, so I can see better what's attached to that carbon. So attached to this carbon, I've got a ethyl group, and a bromo group, and a hydrogen, and then over here, this is a butyl group. Are those groups different from each other? Yes, there's 4 different ones. So that carbon, this guy right here, is a stereogenic center. So this molecule is chiral.
So would that also be the chiral carbon?
That would be the chiral carbon. Chiral carbon, stereogenic center, all refer to the same thing. And for a molecule to be chiral, all it takes is 1 carbon that's chiral. How about on this one? Well, let's do the same thing of moving these around so that we can see them. Here's a chlorine group. I'm just going to block that one out and stick it up here. And then let's just leave the F there. And this H is also attached to that carbon, so we'll pull him down here. So I've got chlorine, fluorine, hydrogen, and methyl. Is this carbon stereogenic? Yes, it is. So that's the stereogenic carbon. Any questions yet? 3-methylcyclohexane. You can't tell by looking at the name. You have to draw it out. So cyclohexane, 1, 2, 3, 4, 5, 6 carbons, cyclo, 3-methyl. What is wrong with that name?
Be a 1.
Yeah, why 3? There shouldn't be a 3 there. It doesn't even need a 1, really. It could just be methyl cyclohexane. I'm wondering if I missed something when I typed that in. Methyl cyclohexane. Does that have a stereogenic center? Well, what's attached to each of these carbons? Hydrogen. So all of these carbons have 2 hydrogens. Does this carbon have a hydrogen?
Only 1.
Only 1. So this carbon has a hydrogen and a methyl group, and then a carbon going this way on the ring, and a carbon going that way on the ring. But does it look any different going to the right or going to the left? No. So we would count these 2 carbons as being equivalent. There's nothing different about them. Yes?
In the book it says cyclohexene.
Cyclohexene. That would fix it. Thank you. 1 little letter. Let's do that. That'll make so much more sense. This one does not have a chiral center. So it's not hexane, it's hexene. That just makes so much more sense. So 3-cyclohexene, well, that's going to be 3, then the double bond must be up here. There's 1, 2, 3. The double bond always starts with 1 and 2. So now we've got 3-cyclohexene. So this guy has a hydrogen. This one has a hydrogen. That one has a hydrogen. And these other guys have 2 hydrogens. So at this carbon, we've got a methyl group and a hydrogen group. And then this is a ring, but is it different if we go counterclockwise versus going clockwise? If we go counterclockwise, we encounter a double bond first, right? And if we go counterclockwise, we encounter single bonds before we get to the double bond. So going counterclockwise and clockwise, I said those backwards, they're different. And so those would count as different groups. And so we would say that that carbon is a stereogenic center. Two,3 dibromobutane. Well, butane has 4 carbons. Two,3 dibromo means there's a bromine on the 2 carbon and on the 3 carbon. And then the rest of these will have hydrogens. Remember, carbon always has to have 4 bonds. So obviously, the carbons on the end can't be stereogenic centers because they each have 3 hydrogens on them. So what about this carbon? It's got a methyl group and a bromine and a hydrogen and this thing. Is this thing different than the other groups on this carbon? Well, this is, there's a mirror image going on here, but this carbon has 4 different groups. Oh, I don't want to use red. So this is one of the groups attached to the carbon, this carbon that we're looking at right here. There's this group and bromine and hydrogen and methyl. Are any 2 of them the same?
Those 2 groups on either side are the same, though.
Well, but this is a methyl group, and this is not a methyl group. This would be a bromo-ethyl group. You see that? So I'll circle this one too. So are the atoms in any of those circled groups exactly the same? No. This is not the same as that. This side of the molecule is the same as this side of the molecule, but that's not what we're looking at. We're looking at this individual carbon. You can only look at one carbon at a time. So is this carbon, is that carbon a stereogenic center? Why not? Doesn't it have 4 different groups? It does have 4 different groups. It is a stereogenic center. So that's a stereogenic center. What about this carbon? Is that a stereogenic center? Yeah, that one is also. Let's use a different color, maybe orange. To look at that carbon, that has a hydrogen, a methyl group, a bromine group, and this big mess over here. It has 4 different things attached to it. So that one is also, this molecule has 2 stereogenic centers. I can see that's bothering some of you.
So you want to have different groups?
The definition of a stereogenic center, stereogenic carbon, is that it has 4 different groups attached to it. If there is a stereogenic center in the molecule is chiral. So this one has 2 of them. This is one with the orange circled groups. None of those circled groups are identical. This carbon is also a stereogenic center. Its groups are circled in blue, and none of those are exactly the same. Okay? This is one of those things that it takes a while to be able to see these things. It's really important. Any other questions?
Why isn't CH3 the same as H3C?
Well, CH3 is the same as H3C. But if we're looking at the orange ones here, what's bonded to this carbon is this whole thing that's circled. It's got a bromine, 2 carbons, and 4 hydrogens in it, is what's attached to this carbon. This carbon has a methyl group and a hydrogen and this bromine, and what's bonded over here is not the same. So let's maybe do something different. If we had CHBr, is this carbon a stereogenic center? No. Because we've got a methyl group and a methyl group and a hydrogen and a bromine. These two groups are the same. Over here, we can't count this as being the same as that because this isn't connected directly to this carbon. There's all this other stuff also connected to the carbon. Okay? Any other questions? Another example, draw the three-dimensional structures for the two enantiomers of one bromo, one phenol, ethane. Okay, so trying to draw three-dimensional structures. So here's the one carbon. That's what everything seems to be on, the bromo and the phenol and the ethane. So ethane has two carbons. And so this is going to have bromine. And then I'm going to draw these other guys. I'm trying to draw the tetrahedral structure. And so it's got a phenyl group. We'll just use pH for that.
That's a cyclo, that's an aromatic ring.
Yes. The phenyl is, I'll stick it down here, pH equals this guy. And then this is going to have 3 hydrogens on it, and there must be a hydrogen over here. So here's ethane, 2 carbons. This is carbon number 1. It's got a bromine on it. It's got a phenyl group on it. And then it must also have a hydrogen. Everybody okay with that? So I drew this using the wedges and the dashes to have the three-dimensional tetrahedral structure at least somewhat be apparent. And so then let's pretend that this is our mirror, and let's draw the mirror image of it. So here's H3, and there's a C, and then this bromine is going up like that, and then the phenyl group is down here, and the hydrogen is over there. So these are mirror images of each other. And this is another part of organic chemistry where it's really helpful to either have a model kit or some toothpicks and marshmallows or gumdrops. Gumdrops are better because they're different colors. And so you can make this out of gumdrops and then show yourself, oh yeah, I can't superimpose those mirror images. Any questions? Yes?
You don't need to draw the ring, you can just put pH.
You can just use pH.
Okay.
You could draw the ring in there if you wanted to. But this is one of the situations where the pH is useful.
Right.
It's just a lot easier. Yes?
Since the bromo and the methyl group are one, how come they're not on the same thing?
They are on the same carbon. They're on this
Oh,
carbon.
okay.
Yeah. So this is carbon 1 and that's carbon 2. So we've got bromine and phenyl on there.
Okay.
Yeah. This is one of those things that, I mean, you just have to be able to visualize what's being represented. And it can be really challenging. And don't give up on it. Keep working at it until it starts to make sense. And you might want to go on YouTube and look for other explanations, because other explanations may make more sense to you. Other people may have better illustrations or better models or computer animations and various things like that, and that can be really helpful.
So that structure was achiral, or was that chiral?
It's chiral. It's chiral because this carbon has 4 different things attached to it. Methyl, bromo, hydro, and
But
phenol.
the other carbon is achiral.
This carbon is achiral. Mhm.